coarser fraction in the demolition waste, because even 80% is used in Finland. It's mostly about using it in earth construction, which is like high volume utilization, but we are looking for high value utilization for the product. So with this idea, we came up with the specific objectives, like to study the practices and guidelines that is followed now. So we can think about reducing the waste that is produced. So to reuse the component of the building materials as such, if we can retrieve them, and then also to study the demolished object, to treat them for better value added products, and also to study about the ripple effects of the project in the construction business in Nordic region. So to know more about the project, of course, you will listen to the interesting and important results of the project today, but you can always follow the website, which is hosted by NARFO. So yeah, keep in touch and have a nice seminar today. Now, Professor Mirja would be giving an introduction about what we do at the University of Oulu about environmental friendly binders. So I welcome Professor Mirja.
Okay. Can you hear me, Jasmine? Yeah, good. So I'm going to tell you about the research what we are doing here related to organic binders here at the University of Oulu. So we are from the Faculty of Technology and from Fiber and Particle Engineering Research Unit. And this research unit has two main research focus areas. We are working with lignocellulose materials, so mostly with nanomaterials based on wood and other lignocellulosic resources. And then we have this research area related to inorganic binders. And here in this area, we have two professors. My group is focusing on the side stream utilization, so the use of industrial side streams as binding materials. And then my colleague, Associate Professor Päivä Kinnunen, is focusing mostly on cements based on magnesium-based minerals. We are very happy this area of inorganic binders and the use of industrial side stream is one of the University of Oulu profiling areas. Here in this figure you can see the profiling areas of our university, and this inorganic side streams is one of those selected as one of the profiling areas 2 years ago, and we have received quite a lot of funding from the University of Oulu and from the Academy of Finland. And there are, I think we were able to recruit 5 more professors or tenure researchers in this field. So when talking about this inorganic binders and the research, what we are doing here, the main motivation comes from the fact that there are a huge amount of different mineral residues generated in all industrial fields. Here is waste statistics 2018 and mineral waste generation in Finland. So you can see basically all industrial fields generate huge amount of waste materials. And this does not even include all the materials, as many of those side streams are not classified as waste. And what is our motivation is that we think that all these secondary resources should be used before we take natural non-renewable resources in use. So this is like the main motivation behind to promote circular economy. All those waste materials or residues, they are coming from our planet, their origin is in our Earth crust, so they consist typically of those elements that are the most abundant in our planets, as you can see here in the right-hand side. So this is like a average chemical composition of our Earth crust. So it consists of silicate, aluminium, iron, calcium, and so on. And the same elements, as I think we all know, can in certain specific conditions, they can form reaction products that harden like traditional cement. So we are able to make binding materials, for example, concrete that doesn't contain any cement in it. And there are different type of reaction products that we can have in our side streams. Calcium silicate hydrate or ettringite, which are also typical reaction products in normal OPC cement. Geopolymers that are aluminum silicate materials produced in presence of alkalines, sodium or potassium hydroxide. And also more and more we are working with materials that the hardening is based on carbonation. Here is more or less what we are doing. So we are quite a big group. We are about 30 people all together, which means that we can have quite a wide research focus. So we are interested in all kind of waste, industrial mineral waste materials and side streams, and also some abundant minerals. And we typically study the chemical composition, the physical composition, the mineralogy. We are trying to understand the reactivity of the materials for those different binding systems. And then we do some treatment, quite often mechanical or mechanical treatment, sometimes thermal or chemical treatment. And the aim in this processing step is to increase the reactivity of the material. And then we design our binding system based on the material properties. So depending on the reactivity of the material and also the chemical composition of the material, we can design our binding system. And what we are aiming is, of course, the use of secondary resources instead of virgin ones, to make new products based on waste materials, to decrease CO2 emissions, and of course to utilize waste materials. And our main applications are in the construction industry. Of course, the amount of those side streams are so huge that we should find the application where the volumes are more or less on the same level. So all kind of applications where cement is used, concrete, but also many other like building materials. We do artificial aggregates. That is also one of the presentations today, where concrete fines are granulated. Internal recycling means that we, for example, for steel industry, we bind together their dusts or sludges to recycle them back to the process. Then stabilization or immobilization of harmful components is sometimes just the topic to make some hazardous waste materials safe to the environment and people. And then the CO2 sequestration is somehow emerging area where we are working quite a lot nowadays to capture CO2 to concrete waste or some slags or ashes. But then we also are working with some specific applications like water purification. Here you can see, for example, 3D printed filter based on alkali activated materials. And here you can see some foam material. So we are developing materials for water purification and for example, for catalytic support materials. So the topic is quite, our research area is quite wide. Here are some key numbers from the last year. So here is our research funding. So about 40% of our funding comes from the Academy of Finland, which we are very happy because then we can do some very scientific research. But then on the other hand, quite a big share is coming from Business Finland and European Union, which we are also very happy because then we can work in collaboration with companies and hopefully see our results in use one day. So I'm really happy that we have different type of funding here, and we are working with more than 30 companies in our current ongoing projects. We have more than 30 companies involved. And nowadays we are also quite active in publications. Like last year we published 38 and almost half of those in top and leading journals according to our national classification of journals. There is a doctoral thesis that have been completed during this time. So we started something like 10 or 9 years ago. Our first project started, and then it took some time to get first publication or even doctoral dissertation out. Our first publication was 2014, and then the first doctoral thesis came 2017, not 18 as here, but 2017 about alkali activation and granulation of fluidized bed combustion ashes. Then we have one doctoral thesis about stabilization of mine tailings, 2 related to steel industry slag utilization, and then the latest one about the use of peat wood fly ash as a supplementary cementitious material. This is one project as an example, and also one of the projects I'm very happy about, because here in this project we study mineral wool. And why I'm so happy about this is that some 5 years ago our researchers Päivä and Juho, Päivä got an idea that this material is very good to be used in alkali activated materials. So it's highly reactive material, and mineral wool and rock wool waste are, at least here in Oulu area, they are probably the only waste material that goes to the landfill. So there is basically no use for that. So then we got an idea that, okay, we could find some solution for this. And now 5 years later, we have a big European project running where the aim is to demonstrate this in a bigger scale in different applications. So it's something where from the idea to the research, and then from the research to the demonstration. So that's what we are very happy. We are somehow in the phase where we do more and more piloting. Here in the left-hand side, you can see housing fair floor casting we had in Lohja this year, and last autumn they made this floor casting by using alkali activated slag material based on the recipe what we have developed. And then one more example about brick production that was done also in industrial scale last year ago, based on the recipes what we had developed. Okay, that's shortly what we are doing. And as I said, this inorganic side streams is one of the profiling areas of our university, and we are now, or we have been working to gather together all the researchers somehow working in this field, and we have this kind of in-streams hub that gathers people together here. So this in-streams hub is like a research community where we have more than 100 researchers from the University of Oulu, and we are doing multidisciplinary research with the main aim to utilize inorganic side streams. And here are the two areas where we are active. There is sustainable material processing, all kind of processing of materials, and also like where we study that how we can affect the side stream properties already in the process where the material is produced. Then we have this construction materials. We are developing materials to prevent environmental contamination, the water purification or catalyst materials, absorption materials, and so on. We are working with inorganic energy materials, recovering battery chemicals from side streams. And then we are working in close collaboration with physics, with advanced characterization techniques. And also what is specific here, we are combining like a Oulu Business School and environmental, what is this? What is this industrial management teams too. So there is not only this material research, but also business research. One example, this is I think the last slide, one example about the most recent project that we received from the Academy of Finland, where we study municipal solid waste incineration ashes. So this project will start at the beginning of next year, and here our aim is to do treatment to control the metal recovery and also the reactivity of material for cementitious systems. Then there is the metal recovery that is not done by ourselves, but by our colleagues here. And then we study the cementitious reactions of this mineral residues that is left after the metal recovery. That was my presentation. Thank you.
Yes, if you have any questions for Professor Media, so you can either ask or type in the chat. We will wait for a minute and we will move on to the next presentation. Okay, if not, hey, I just remembered I didn't introduce myself. I'm Priyadarshini, you may know by now. So I'm Priya and I'm the project manager for this DeConcrete project at University of Oulu. So yeah, so our next presenter would be Dr. Iveta. She's from UIT Norway. She would be presenting about current policies and utilization of recycled concrete in Nordic countries.
Okay, I hope you all can hear me. And is it okay?
Yeah.
Yeah. And then I will share my presentation. Okay. So my name is Iveta Novakova, and I work at the Arctic University of Norway, and I'm a leader from UIT for the Concrete project. So I would like to present some results from our research work connected to the concrete. First, work package from the Concrete project is focusing on legislation and possibilities of recycling or reuse. So it's very important to know what are the possibilities and the levels allowed by government, because that's what has to be followed. So I would like to mention some motivation for such a study, such a part of the Concrete project. So we want to, our aim is to better utilize the resources which normally would be landfilled and will reach the end of the life, but we would like to integrate it into the circular building material flow and also circular economy, which will bring benefits not only for society, but also for nature. And so we actively want to support the good practices and reduce the negative environmental impact. Within DeConcrete, we are, the partners are from Russia, Norway, and Finland. And the reason for cooperation is the common climate conditions. So it's very harsh condition, winter is long, low temperatures. So the practices deviate from, for example, like other parts of Europe or other continents. And also the distances are big. So some practices which can be used in highly populated areas like Belgium cannot be applied here in north because the distances are huge. So that's why we established this consortium and look into problematics in the region. Legislation was published within one article within this project, and it was published in Nordic concrete research, which is suitable application for such a focused topic. So outline of my presentation, I will mostly present the data from the article. So I will start with introduction, demolition actions, construction demolition waste management, and then I will conclude the outcomes of this study. Data obtained for this article were in a form of questionnaire, which was sent to all partners, and each partner filled up the questionnaire, and then it was summarized into the article. So to introduce why we are now at the a time when we want to recycle, from literature you can see that the building boom is actually moving. So it first was in Europe and then followed US, America, and then it's moving to Asia. That's why China is now has high consumption of building materials like concrete and steel. So just that because the periods for the biggest boom are moving. So it's as it is started first in Europe. So we are the one who are starting to implement all the practices because we are already demolishing. There is no that big demolition yet in China because they are on the phase of building. So even there are some practices already implemented, but still they are delayed. And we can see it also here from the diagram with the production of steel and concrete. So it's growing simultaneously same way as the growth of population. And there are some predictions for future. So construction demolition waste management, I will mostly focus on our three countries of the Russia, Finland, and Norway. And also I will put in some data from European Union as those are quite well processed. As it was already presented, the waste management in Finland by Merja, you can see all data are slightly are slightly different because there's a lot of sources and it's very hard to get the data about the waste, how the waste streams and to capture all the waste streams because sometimes they are recorded, sometimes not, and there are different conditions for the handling of the waste. So globally, about 35% of the whole waste is construction demolition waste, which is very bulky and heavy material. For European Union, it's about 33%. It's 374 million tons, excluding soil. And these data are from 2016. Because of low amount of recycling, European Union imposed a limit for 70% of all material reused or recycled by 2020. The data from this are still under review if the country is reached or not. And then there is a study which was conducted by European Environmental Agency that they estimated 96% of all mineral waste can be recycled. So that might be the next aim in future, which is very high level of recycling. When the 70% like recycled level of recycling was established, the 2 documents for European Union came out and were helping all the countries, also the countries which follows, because Russia and Norway follows also European legislation partly. So these documents were published to support the change. Overview of some data from waste management. So how much in percent was recovered on land or landfill. I will talk about the Finland, Norway, and Russian Federation in detail. So you can see that the levels are really changing, and there's many sources where you can collect the data. Different sources, different data. It's sometimes hard to find out if the soil is included or not. So most countries are above 50% or around it. The countries which are not even not at 50%, they are trying to implement as many as possible of new technologies to increase the recycling of construction demolition waste. So in detail, the generation of waste in Finland, it's 16 million tons, including soil. Those data are from 2011 and 12, so they're rather old. And even by then, there was a 77% recycled. So the movement of material is also hard to follow. So if the material was transferred or used only on the same spot, it's not recorded. So then if you look into the Norwegian waste management, so there is 1.95 million tons, excluding the soil. The recycling in 2019, the ratio of recycling was 46%, but that changed by 2020 because of change of the legislation, which I will talk about later. And so Norway was on very low level of recycling due to restrictions by the regulations. And when we look into the Russian recycling, there is a 15 to 17 million tons of construction demolition waste, excluding soil. So there is a high, it's big amount of the waste and very low ratio of recycling, only 5%. But there is a big growth and intention of the increase of the recycling, and the growth is approximately 25%. The 5 drawbacks for the why we are not able to recycle properly is because the regulations are not really clear, and you will see later. I will present the data from 3 countries, which are completely different for each country. And then also there is no clear government or the part of the government which is taking care of this, because you are basically changing waste into the material, and that's a problem, this change of the status. And then there is a lack of fundamental data in CDW, construction demolition waste management. As I mentioned, it's very hard to follow all the sources and make a robust data about the waste streams and quantities. Also, the management of or demolition is not usually included, or the budget is not adjusted for the demolition, and it's just like indispensable part of the construction, but the demolition should be more lifted up and should become a comparable part to the whole construction project. And then the facilities for construction demolition waste recycling, they are struggling to grow because there is so many legislations they have to follow, and to get all the certificates, it's usually very time taking and very difficult. So I separated the presentation in 2 sections. So it's demolition action, which is contained of demolition, pre-demolition audit, planning of demolition, and demolition itself. So I will go briefly through legislation of our 3 countries who are in the project. And you can see for pre-demolition audit and also demolition itself for Russia, there is no clear legislation for that. So they are basically using the legislation for building and just making it in reverse. So they are following such a legislation and just deconstructing in the opposite direction as deconstructing. And the most common materials in Russia for building is calcium silicate and clay bricks, stone, concrete, and reinforced concrete. You can see that, for example, those are most common materials. You will see difference in our in other 2 countries, and I guess it's very much deviating in other European or countries around the world. So pre-demolition audit in Norway, there is legislation available from Building Research Design Guidelines. So this is like direct translation of Norwegian website, which is slightly more better formulated. And there are courses for auditors. So from different regions, so you can get education for being a pre-demolition auditor. And then there are some conditions what you need to include in the report, and also what the report should contain. And the most common building materials in Norway are wood, concrete, reinforced concrete, and lightweight aggregate blocks. Yeah, so also the different materials are used for different parts of structures, which is important for selective demolition. For Finland, we have a pre-demolition audit covered by the building law 127 paragraph and the 159 paragraph. There is a different way of handling if it's a hazardous material such as asbestos. And then the most common building materials in Finland are wood, steel, brick, concrete, and reinforced concrete. So when it comes to planning of demolition, as I mentioned, in Russia, it is covered by the construction regulation. So you reverse them and you need to assess the study, you need to develop the study of existing documents. Then you need to do visual assessment and detail instrumental examination. And stage 4 is a survey results. So yes, for Norway, we have also regulations to follow, which are stated here in this slide. And the technique, there are different techniques for demolition, and also all the materials has to be assessed, sorted, quantified, and it needs to be clear what is in the building, if there are any hazardous materials or not. Finland is very particular about the asbestos, as it was used often for isolations. And there is the courses for auditors, which are also meaning this planning the demolition. Here in the table, we have levels of contaminants which the material can contain, which can be recycled. So there are limits usually for the inert waste, which can be recycled. And as I mentioned, for Norway, the chrome level was increased in 2020. So before it was the level for chrome 6, which is harmful for lungs, was or for human, it was 2 milligrams per kilogram, and now it's 8. So that allowed that since 2020 we can recycle more in Norway. I need to speed up as I'm slightly on the edge. So demolition itself, there are regulation again, especially for the noise and dust. So all this needs to be monitored, and all the regulations are different for urban areas and for the countryside. The same for Norway. Again, the levels are different for the countries. They're very strict in Norway. Finland usually follows the European like recommendations, or they have their own national. And then yeah, important to mention that in Finland there is already a big part of demolitions are done by selective demolition, while in Russia they are mostly reusing the windows or some such elements. And in Norway those elements are not reused because they doesn't fulfill the present standards and regulations for the thermal and acoustic levels. Then I move to the construction and demolition waste management. So that again, two parts: handling of construction demolition waste and utilization of secondary raw materials. So when the waste is changed into material which can be reused and used again in construction. So when we come to the handling, there are some charges, how much you have to pay for landfilling or for delivering of the material in the recycling centers. And there in Russia, there is 243 recycling centers. So there is a very big potential to recycle, increase the capacity of recycling. In Norway, there is very few and almost none recycling center at the moment, and there is a very big attempt to establish them. And there are recycling centers for soil, for example, but not for concrete yet. In total, there's 64 landfills in Norway. And in Finland, there is about 200 landfills, and there is a well-established recycling system and very high level of material is recycled. Where the secondary raw material can be utilized, mostly I will refer to the concrete because this project is focused on a concrete recycling. So in Finland, you can utilize concrete in the concrete is mostly utilized, or the recycled aggregates from demolition of concrete are utilized in the road structures as a filling material. It is also allowed in concrete production, but that is not integrated in industry in a large scale. For Norway, it's mostly the same. There is a legislation which is followed for integrating it in roads and as a filling material. And there is a big attempt to integrate it in a concrete. So there are regulations which are coming from standards 12620 and EN 206. New 206 for Norway, there is a national annex which will allow the higher amount of replacement, and some new rules will be applied which will allow the higher integration of recycled aggregates in concrete. And in, okay, I will miss somehow Russia, now I have Finland again, I think. Yeah, so I'm sorry about that. Yeah, so in Russia is the same trend. And I'm very sorry. And they have a different legislation about the integration in concrete. And that level is also rather low. So one aim of the DeConcrete is to increase the level of integration of recycled aggregates in the concrete. Just for like overview, the prices of the natural aggregates and the recycled aggregates. As you can see, there is no price for recycled aggregates in Norway, as it is not industrialized yet. And so the conclusion, in the end, I will go through just the amount of the waste which is produced and the ratio to the recycling centers and the places to for landfilling. So there's a big potential in Russia because they have a lot of recycling centers, which is very good. The low recycling ratio in Norway from 2019 increased over to 2020, thanks for the change of the legislation. And then Finland is doing very well. They fulfill the European regulations. In total, it's 80%, and they are still trying to improve the selective demolition. And what are the proposed 5 countermeasures to improve the recycling and reuse of construction demolition waste. Says enhance the effect of regulation, so make a clear overview what regulation should be followed, especially for demolition, and a collecting of the resources which is connected to selective demolition. Enhance, so take seriously the handling of the construction demolition waste as the material which can be still used, not the waste which needs to be landfilled. And promote construction demolition waste recycling, so spread the knowledge, which is very important, and have very efficient implementation of the waste material, and change the fees, because if the material will be delivered to recycling center, has bigger potential than to be landfilled. Yeah, thank you for your attention. That's yeah, and sorry for taking more time.
Thank you, Iveta. So there is a question already in the chat box. Thank you very much for your presentation. Is there any recommendation in Nordic countries? For the use of recycled aggregate, that is percentage of replacement with natural aggregate in fresh concrete?
Yes, so there is a regulation, because Norway is following the similar or the core standards as are in European Union. There is a national annex, which, as I mentioned, is going to be changed, and the rules will be more kind of acceptable for the replacement. So what I know from now at the moment, that there is only stated percentage, and what the input material, which means the recycled aggregates, has to fulfill, which is the standards are prepared for natural aggregates. So it's for recycled aggregates there are some rules, but it's hard for them to comply with it. But in a new 206, it might be implemented that the material will be tested as it is already, not the aggregate separately, which will help integration of recycled aggregates, higher levels of the recycled aggregates.
I think we see that this all over Europe, the standards are a problem for the researchers, because when we do the research, we find out that we can utilize much more of the recycled aggregates than what the standard allows. So I think going through the national annexes and this way will be much faster to utilize the products better than to change the standard, because changing standards takes a lot of time and is very difficult. So to have the work done in the national annexes, and I think in a project like this, if we could influence to have similar national annexes in our countries, then it would be easier to implement this as a standard later. But we also see another thing, and that is that from the demolition waste, a lot goes missing. Fines, sludge, nobody knows. If you look at how much is produced and how much is landfilled or reused, there is a big discrepancy between this and that. So what happens with the rest? Nobody knows.
Yeah. So yeah, maybe we will move on to the next presentation, keeping the time in mind. So our next presenter would be Dr. Kosman, and he would be presenting about demolition methods of building components, traditional versus alternative methods. And he works for the research organization called Sintef from Norway.
Thank you, Priya. I'm going to share my screen. Just a second. Share. Okay. So, hello everyone. My name is Cosmin Popescu, and I'm representing Sintef Narvik. And today, I have prepared a presentation regarding demolition methods of building components. A short comparison between traditional and new alternative methods that we proposed in this project. So I'm going to give you a brief overview of the broad scope of not only this project, but also other projects that goes hand in hand with DeConcrete. So we are interested to find ways to reuse building components, mainly structural members. And we have done some literature review to assess the demolition methods, both traditional and as new alternative methods found in other industries other than construction industries, to see if we can implement or further develop those methods to be able to help us find new ways to demolish construction elements. And then we were looking for demolition energy, because this is one of the main barriers in adoption. Then we went further to identify the case studies that they were used in concrete elements. And here, Netherlands is a good example. Quite broad experience in reusing concrete elements in comparison with many other countries. Focusing also on recurrent elements in buildings with high reusability. That will give us much more incentive for the construction industry, rather than focusing or trying to reuse any kind of elements. We're going to see later on which elements we found the most feasible for reuse in new construction. And then finally, about the quality assurance through non-destructive methods and selective proof loading to be able in the end to issue a new, as we call it, rebirth certificate. And this so with this we can start looking through the background of demolition methods. So we have three main categories. We have the progressive demolition, where we have a removal of the structure in a controlled manner, and this is very good for confined spaces. And then we have the second one with the deliberate collapse mechanism, where you identify the key structural elements and you target those ones. This is suited for detached buildings with enough space available around. So these two categories are for complete demolition, but we are not really interested in this. We are interested in the last one, which is called deconstruction. So here we looking for deliberate removal of elements. It's basically the reverse process than that of the construction sequence, in order to maximize the retrieval rate of the structural members for future use. The demolition process, it's relatively well known. It has been first documented in 1773 by implosion. This is the first case study available in the literature. There are standards available for demolition. Unfortunately, nothing exists for reuse or how to deconstruct. And there are many barriers that we identified. Among them, the most important is the supply and demand issue. There are four main tasks in demolition, and we are going to focusing on demolition of the structural skeleton. So to go into it, demolition techniques, we have the mechanical methods, we have the abrasive, we have the explosive, and there are a few others like thermal, electrical, chemical that are not used in that extent. So for mechanical demolition, we have the impact hammers. First are manual impact hammers, best for dismantling the elements. There is no need for specialized personnel, but unfortunately it requires high physical effort and high discomfort due to noise and vibration. So you see the amount of noise generated is quite high, and it will also introduce uncontrolled cracking. And this is not good if you want to reuse the concrete elements in other buildings, as you want to retrieve, as good as possible health these elements. So you have different type of hammers, like pneumatic, hydraulic, electric, with different kind of impact force and vibration and noise generation. Then we have the ones that are machine mounted. This is for heavy demolition. It can go up to 10 tons. The hammers, which are attached to hydraulic excavator's arm. We have hydraulic and pneumatic. So you can see that pneumatic is more suitable for urban areas, and also the pneumatic hammers can be fitted on light carriers, and does not require hydraulic connections. Then we have other mechanical methods by pusher arm, methods by wire rope pulling, and by and these are, as you see, demolition methods. It's not really possible to retrieve elements by these methods. Then we have mechanical method by hydraulic crushers with long boom arms. We have different attachments. We have hydraulic shears, pulverizers, and multi-purpose jaws. Here we see an example with hydraulic scissors, concrete pulverizers, demolition jaws. Then we go for abrasive methods. Here we have diamond core drilling, diamond wire saw technique, and finally the diamond saw disc sawing. And I would say this one is the most common in element retrieval, because you have a controlled way to dismantle the elements in comparison to the previous methods. And finally, some handling methods, handling of demolition material, grapple tool to sort the elements on site, hydromagnets for separating the reinforcement from the concrete, and then some a bucket screener to sort this and separate crushed concrete and recycling material. And before going into alternative methods, we have to look into the current status of end-of-life scenarios for different materials. We have concrete, timber, and steel. And we can see the degrees of reuse, the degree of incineration, the degree of material that goes to landfill. And we can clearly see that concrete is mostly reused by downcycling, so not direct reuse. We see a small percentage for steel, 6% it's reused, and 13% for timber, but nothing documented according to this study for concrete. So it's in very small amounts. And this is mainly, as I mentioned in the beginning, mainly due to the existing barriers for use, which are three main ones: logistical barriers. So then, as I mentioned, supply and demand, liability barriers for structural engineers, who is gonna guarantee the performance of the elements, And then cost barriers, both in terms of energy, but also that the clients are expecting these elements to be cheaper somewhat than building with new elements. So there should be clearly an incentive for overcoming these barriers. Also, if we're looking into recycling and reuse in terms of demolition energy, we see that the energy required for demolition is relatively small compared to the overall life cycle energy. And the demolition for reuse requires actually more energy. And if we look into concrete, it's about 40% more energy needed when reusing compared to when demolishing or recycling. So this is a need for a new demolition methods. So, and there we have also another slide here. Why do we need new demolition methods? So as I mentioned, reduce the demolition energy, but we also need faster and predictable demolition techniques and methods that reduces the vibration on site and that can avoid micro cracking in structural members for future reuse. And currently, some of these aspects are dealt on site with existing methods by having crane suspended curtains for dust and noise minimization or water pulverizers. And we were looking for different methods as alternative to what I already presented. And we thought that this one could be a good candidate to develop further. And this is hydraulic fracturing or fracking, which is used in extracting the natural gas, natural oil. And here the method works by fracturing the rock using water, sand, and chemicals. It has an advantage that there's no dust generated, is noiseless, but it requires a large quantity of water. And the question was if we can develop the method to weaken the concrete elements. And then we're coming to discussions what kind of elements this could be the best applied. And the legislation was one of the barriers that we encountered. So it's very difficult to reuse, even though you develop a method to demolish or deconstruct an element, it's going to be very difficult to use those elements in new construction because of the legislation. It is very difficult to comply with the current legislation. And in Norway, they came up with a guideline that will, we hope later on, will become a standard for reuse of hollow core slabs. So you see here, first of all, I should mention that prefabricated buildings are the most suitable for reuse rather than monolithic structures. And from this, we have the prefab beams, columns, or slabs. And since the beams and the columns are very sensitive to the load cases, they are vertical elements. For example, the building, in a building, the columns are vertical elements, and they collect area load according to certain area, floor area, and then you have a different amount of stories. So in the end, you're going to end up with either under-dimensioned or over-dimensioned elements, which requires over-dimensioning the foundation in the new building. But the horizontal elements, like hollow core slabs, they are not as sensitive. The live load in structures are quite similar from one building to another. The range is between 2.5 and 5 at most in office buildings. So this makes them as a good candidate to reuse them. So we were focusing on prefab hollow core slabs. And the problem here was the removal of the overlay, the top surface. We came up with three methods. First is the Hydra split, which is developed upon the fracking method. And here we have some nozzles that penetrates the certain thickness. As I mentioned, the overlay, the top overlay, which is up to 5 centimeter thick. So it can penetrate this thickness within the hollow core slab. Then we have the hydrodemolition. Here we have the nozzles with high pressure, water pressure that can remove the top layer. And finally, the pulse water jet. And this the whole element is placed underwater, and valve pulses the pressure so that the layers are divided or that the concrete is crushed. I don't think this is quite feasible, so we were focusing on these two main solutions, and currently we are in the phase of developing the method and trying it in the next coming months, I guess. So there are some master students doing their thesis on this, and we hope to find out that these methods can be used and further developed and transformed into a commercial product. So thank you very much for your attention.
Thank you, Cosmin. So is there any question for Cosmin?
Elements will be delivered as soon as we have the new painted floors.
Okay.
we have them at Chopsvik, the ones we are going to use.
Yes.
So these experiments will be done.
Yeah.
And we are thinking, me and Bob, about adding high voltage electrode pulse.
Okay.
Also into this.
Yes.
So we are talking to the high voltage electricity guys at the university. They can help us devise. We are thinking of a product where you connect to the rebars in the top layer.
Okay.
And we will, but I would like to try.
Yes.
Then we will try the fracking and high voltage electric pulse to see if this will disperse.
Yes. Hopefully it will not damage the whole element, because there's no use.
Okay, there is no question. Then we will have a 10 minutes short break, and then we will continue more. Okay. Okay, here is a question. How many times can concrete be recycled without compromising the structural strength?
Well, how many times? We know that the concrete elements are designed for a certain lifespan. Usually it's 50 years old, but we think it can bear another life cycle, and that's the idea of this rebirth certificate. So we are trying to develop new non-destructive test methods so that when it reaches the design life, then we apply this non-destructive testing. We see that everything is looking good from the material point of view, from the environmental point of view, and from the structural point of view. And then we are able to reissue another target design line. And you don't know how many times this can be done, because the elements would most probably be used in a different location with different environmental it will affect the environment, will affect the methods in an unknown way, so to say. And it's going to be difficult to reevaluate in advance, in my opinion.
Okay, so I hope that answers your question. And so we can have a short break for like 8 minutes now. So we will be joining, I don't know your local time, so it's better to keep it like after 8 minutes. So yeah. So we are back, and thanks for waiting for the coffee break. And now again, we are back with Iveta, and I think the second half of the presentation are more into the utilization and recycling of the concrete waste. And now the first presentation is about recycling concrete fines as supplementary cementitious materials. So again, to Dr. Iveta.
Okay, hello one more time. Let me share my screen and so I hope all of you managed to refill your cups with coffee or tea, and we can continue with the seminar. As Priya mentioned, now it will be more focused on utilization of the materials and the possibilities where they can be utilized. So one of the idea is to use this recycled the fines from the concrete productions as a supplementary cementitious materials. Outline of the presentation is some introduction, and then the definition of describing the sources of supplementary cementitious materials, preparation and whole concept within the DeConcrete project, and analysis of input material, which are very important in this case, and then design of mixes of individual stages, and some results discussion and conclusion. Presented data will be published soon in scientific articles, so I'm not gonna go very deep in the results, more introduce the structure of the program or the testing plan and some part of the data. Again, introduction, why are we looking into such a issue? We are, as it was mentioned, trying to utilize as much as possible of the waste originating from handling or processes connected to the production of building materials. We also want to promote the reduction of the CO2, which is connected to the cement production. So one idea is to reduce the content of clinker and replace it by supplementary cementitious materials. Nowadays used supplementary cementitious materials are fly ash, blast furnace like silica fume. There are several others like calcinated clay, but some of those are already exhausted or becoming scarcity. So there is a need to look for another types of supplementary cementitious materials, and also focus on the locally available supplementary cementitious materials. As in, for example, in Norway, there are no sources of fly ash, and presently for Norcem, which is the cement producer in Norway, the fly ash is supplied from Turkey, which has quite significant impact on the CO2 due to the shipping of the supplementary cementitious material. The sources of supplementary cementitious materials used for this study and within this project, the concrete project, were collected in Norway Finland and in Russia. Due to the COVID, the sample from Russia was not possible to be obtained to transport the sample from Russia to Norway. So therefore, this part of testing was done in Arkhangelsk University in Arku, and so it was very hard to coordinate all the material, input material, cement type, admixture. So it was quite challenging just to not have all the things at one place and test them together and do it in more laboratories. Sample 1 and 2, which is marked NBE and Yaro. Those are sludge materials which origin from the producing of the concrete. So NBE is from the precast concrete production of hollow core slabs and from the cutting of the hollow core slabs mainly. Then Yaro type of sludge is originating from the production of precast concrete elements and also washing of the concrete trucks. And this source is located, the company is located in northern Norway. Type called Priya is the fines which were produced in Norway, in Finland, and those are from the crushing of the concrete, waste concrete and production of recycled aggregate. So those are fines which were received, and all these materials were with the maximum particle size 0.125 millimeters. And the type from Russia is also from the crushing of concrete from demolition. All the powder materials used within this study were collected as a sludge. So therefore they were, or two types of sludge were collected in a very wet state. So they were dried, milled, not in purpose to mill to reduce the particles, but to like pulverize it because they were glued together because of drying. And then all the types, including the fines from recycled concrete aggregates, were received to obtain the same maximum particle size. This study started with analysis on input materials and followed by paste testing, mortar testing, and concrete testing. This is like whole concept of the material evaluation and integration in the building materials, or like the potential use. So the analysis of the input material, this supplementary cementitious materials originating from the concrete handling or production. So as it was mentioned, all were under the 0.125 millimeters. Fineness of powders, density, particle size distribution was evaluated, and then also the chemical composition by handheld XRF and stationary XRF, and then mineralogy was analyzed by XRD. Design of the mixes. So for this presentation, I selected this part with testing of the mortar. The mix design was, or the structure of mixing was designed as a replacement of cement by 10, 30, and 50% by volume of cement replaced by the supplementary cementitious materials. And there were differences in the density, particle density of the input materials. So therefore, that's why we didn't replace it by weight, but we did replace it by volume percentage. Due to to maintain some system, it was set to keep workability in some range and also air content. Therefore, we used the super plasticizer and air reducing agent to maintain the water on the same level for all mixes, and the workability adjust just by super plasticizer. And in case of extensive air content, the air reducing agent. So testing methods which were used during this project or this set of test evaluation of supplementary cementitious materials. So on a fresh mortar and paste, it was tested standard consistency, setting time, and on mortar density, air content, and workability. Those were the control, or air content and workability were controlled within certain borders or range. And hardened properties of mortar, we check density, flexural strength, compressive strength, and shrinkage of the mixes with 10% replacement. Next following stage, we will be focusing on preparation of concrete. So that one is not done yet. So to publish few of the, or present few of the results from this testing, I will start with evaluation of input materials. You can see that there are differences. Unfortunately, I haven't had the Russian testing and samples, as those or all the fine analyses were done in Oulu University, and the blending and preparation of pastes was or paste and mortar was done in UIT in Norway. So the stationary XRF analyzed also oxygen, and that was different from the from handheld XRF, which is not able to analyze oxygen. And we can see that there was a higher content of silicate in the silica in the fines from crushing of the concrete than in the sludges from the concrete production, while there was a higher content of calcium in the sludges due to the more leftover of cement paste, especially in case of Yarover, that sludge is including washing of the concrete tracks. Fineness of the materials, so they were analyzed for particle size distribution, and for comparison, Portland cement is added in the figure. So we can see that fines from production of cement, of production of concretes, are much finer than the fines from crushed concrete or crushing of concrete production of the recycled aggregates, which was actually verified by the fresh properties of individual mixes, which we can see here. So to achieve good workability or to maintain consistency within a given range, which was 220 to 265. So to maintain this flow, we added plasticizer, and also some types of the sludges were adding air content due to the fineness or due to the reaction with the matrix. So we were using air reducing agent, and as you see for Priya type, so fines from the crushing of concrete, the replacement of 10, 30, and 50%, the air content was increasing accordingly. So some few data from the hardened concrete testing. So we can see I gave an example of NVE type, 10, 30, 50% replacement compared to the reference mix without any, purely with the cement. And there is an obvious reduction of the strength, compressive, and also flexure strength. Nevertheless, the 10% of replacement doesn't have significant effect on strength, and follow the development of strength as for the reference sample. And with 50% replacement, that's a rather high replacement ratio, which had significant impact on the compressive strength. As we are talking and we are trying to implement this into the industry, then replacement of 50% might not be efficient because there is not enough sludge to put in the production. So actually this 10% might be efficient to consume all the sludge produced in the concrete plants and still maintain the production with the high quality. So we decoupled this testing from concrete to mortar just to test the mortar and impact of the fines on mortar. And as the next step will be the combination with fine and coarse aggregates. Furthermore, the impact of the supplementary cementitious materials on the development of strength. It is visible that there is a delay of the hardening from a reference mix. So I put as a reference the 28-day strength, and then there was a slower development of strength for 3 and 7 days of the mixes with a high replacement ratio, but there was a higher gain after 90 days. So there is a obvious effect of addition of the supplementary cementitious material in the long term, and it's not achieved after 28 days. To conclude on the topic, so as I mentioned, the testing of the fines from recycled concrete aggregates was performed in Russia at Narva University, and the rest was conducted at UIT. Therefore, most of the results will be given in percentage, as it was hard to match exactly the properties of all input materials and check or focus only on the properties of supplementary cementitious material. So we can see that the fines from recycled concrete aggregates doesn't have a significant impact on the workability, while the fines from sludge reducing the workability and has to be compensated by the addition of superplasticizer. There was a visible inblend of the air when the supplementary cementitious materials were added, and therefore we maintain it with the air entrainer. And the same actually might occur with the concrete production. Therefore, we need to keep it in mind that there might be such an effect. And yeah, then as I already mentioned, the impact of supplementary cementitious materials on the strength development, that again, it might be more useful as with all the supplementary cementitious materials, that the strength after 28 days is still developing and doesn't reach 100% of the like provable or significant strength. And the 10% replacement has no significant impact on the hardened properties, and also might be sustainable replacement ratio for the concrete production without any significant impact on the properties under the industrial production. So the further research will be now continue from mortars to concrete. And thank you for your attention.
Thank you, Iveta. Do we have any question for Iveta?
Which cement was used?
We have used cement CEM2 with slag produced in Denmark.
Okay.
Thank you, Iveta, for making me famous by naming one of the samples after me.
Well, it was the laboratories who gave the name, so I just follow it.
In the publication.
Everyone who visits our lab see all these Priya samples.
So that's how I became famous. Now I understood. Okay. So yeah, if there is no question, let's move on to the next presentation, which is by Kalle, and he's a PhD in the project DeConcrete, who's working with in University of Oulu, and he's working on the concrete fines. He would be talking about developing granulated aggregates from recycled concrete fines. Yeah, you can come. Yes.
Microphone on.
Yeah, it's on already. So
They can see me.
no,
Is that okay?
everything okay.
Okay,
You can
so
start.
hello, I'm Kalle Kursula, and I'm PhD student from the Fiber and Particle Engineering from the University of Oulu, and I have been working with this granulated aggregates from recycled concrete fines. And so let's start. So as an introduction, as Mirja told us that those fines are not utilized fully yet when this recycled concrete is divided to the coarse and fine fraction by the size. And here are figures from the laboratory about those coarse and fine fraction of recycled concrete. And then I have been working with this granulation of waste powder, concrete powder, with some industrial residues, mostly from the steel slags and paper mill, also as a co-binder. And then I have tried to find suitable curing methods for the granules. For example, this carbonation could be suitable method for that, because it is also possible to sequestrate carbon dioxide from the atmosphere to the granules. And then I have done some engineering tests to the granules and also study the mineralogy of the produced granules. And I have two cases here. In this first case, I have done the granulation of waste concrete powder. I think this is the same material that Iveta has named Priya. It's Finnish waste concrete powder. And I use ladle slag with different amounts of co-binder, so 0, 10, 20, and 30%. And in the granulation process, I used water in the binding agent, and I tried to produce granules with diameter of 5 to 8 millimeters, because we found some commercial aggregates which are similar size, and it was easy to compare them. And in the figures are this concrete powder, and then how it looks when you have a fresh granules produced from that. And here are XRF analysis of this concrete fines and ladle slags. And as we expected, it contains calcium and aluminum and silicon mostly. And here are then I used 3 different curing methods: that normal curing in the laboratory conditions, and then humidity chamber where the relative humidity is quite high, and then it is carbonation chamber where this accelerated carbon dioxide concentration. And in the figure are those granules after curing, so it can be noticed that clearly some reactions happens during the curing because the color changes. And here are the strength of the granules after 28 days of curing, and as a function of this ladle slag content. And as we can see that when ladle slag content is low, like 0 to 10, this carbonation curing is most effective way. And when the ladle slag content increases, then this humidity and normal curing are also quite suitable ways. And I found this biggest strength with this humidity chamber with 30% ladle slag. So I think that high amount of ladle slag produces hydration reaction, so it makes the granules strong. And this, we compared this to the commercial aggregates, which have a strength of about 55 newtons. So we can observe that most of my granules are stronger than those ones. And here are the density and water absorptions of the granules. And the limit for the lightweight aggregates is like 1,200, so all of them are below that limit, and so they can be classified as a lightweight aggregates, which is a good thing. And also this water absorption behaves quite inversely compared to the density. I think that the water absorption of those commercial aggregates was something about 20%, so they are mostly below or similar to that. So the properties are quite comparable. And I think the TGRS analysis, thermogravimetric analysis for the granules, and to study the calcium compounds. And we can see that the amount of calcium carbonates increases when the carbonation curing is used. So I think that these results prove that carbonation reaction really happens in the granules. And here are, for example, some microscopic images of the surfaces of the granules. So we can observe that with zero ladles, like a normal curing, there are many cracks in the surface, and compared to the carbonation, the matrix is much more denser, and also those granules were stronger ones. And this is my second case. So I have used this precast concrete waste from Norway. I think that it was Jaro in Iveta's presentation, and also this blast furnaces like paper mill as and the biomass fly as a co-binder. Here are again the components of those, but again they contain high amounts of aluminum and silicon and calcium. This time I make quite many preliminary experiments before I found the suitable composition for the granules. So I did totally 12 different mixes, and they always contained blast furnace slag and 10 ether or paper mill ash or biomass fly ash. And this time I used this 8 molar sodium hydroxide as a binding liquid in the granulation because water didn't work. And this time I only used the oven curing at 60 degrees because that was only curing method that was suitable for this material. And here are again the 28 days strength results for the granules, and I think that this biomass fly ash was better co-binder for this material. Again, there are quite big variation, but at least with the high amount of co-binder, the granules are stronger compared to the commercial lightweight aggregates. And here are some properties like this density and porosity and water absorption. And I think that they were quite like in the accordance with the strength test results. And also these are again those lightweight aggregates according to the bulk density. And I think that porosity and water absorption are as good or better compared to those commercial lightweight aggregates. That is the reference material. And well, these are the first 2 articles of my PhD thesis. So now I'm working with the recycling of this geopolymer concrete. So I have changed the material again. And according to the preliminary tests, I have noticed that granulation carbonation could be good technology for this. And now I'm especially working with the optimization of the particle size of the material for the granulation process. So that was my presentation. Thank you.
Okay, thank you, Kalle. If there is any question for you, let's see. No, there is no question.
Nobody is interested.
No. Your presentation is very clear that no one had any doubts.
Yes.
So that should be the reason. So yeah, If you have question, just post it at any time. We can answer until we are here. So our next presenter will be Deepan. He's also from this research organization called Cementitious from Norway, and he will be presenting about testing methods on granulated aggregate produced from ready-mix concrete returns. So I will leave the floor to Deepan.
Thank you, Priya. I will present my screen.
Deepan, you're muted maybe.
No, I just unmuted myself. Can you hear me?
We don't hear you.
Okay. I unmuted myself.
No, I can, do it here. Oh, okay, now.
Can you hear me?
Yeah, we muted our system, sorry.
Okay, yeah. Thanks. My name is Deepan Bista, and I'm a researcher and a PhD candidate at Sintef Narvik. I've been working with concrete dams, concrete and recycling of concrete here at Sintef Narvik. First of all, I would like to apologize to you all for not being able to meet you all in person, and especially to Iveta and Boyarna, with whom I plan to travel together. But I had to make that choice because my son and wife are both sick, and we even had to take a trip to the hospital last evening. And it seems like I'm getting that as well. So probably you didn't want me around you all, but sorry for that. Today I will walk through the thought process or development process of a test method for recycled aggregates. Actually, to speak more correctly, we adapted a standard test method for our recycled aggregates at the lab. And this test was more related with a project called Circulus, but it is also very relevant in DeConcrete, as we are talking about recycling and recycled products. So a brief background of what we did in the test. We were testing dry washing of concrete trucks. Today, the return concrete in the concrete mixture are either dumped or used as used for production of blocks. And when they are dumped, they are source of huge waste, and also the concrete trucks are washed with water, and they are also a source of huge wastewater, which needs treatment. So Mapei, a commercial company, probably you know about this, developed a product called Recongero, which can be added on the concrete truck, on the return concrete, and it's a polymer-based product which absorbs the water in the concrete and also accelerates the hardening process. So when we mix the return concrete with this product, we get after 3-4 minutes of mixing in the drum, we get recycled aggregates and a relatively clean drum without sludge. These aggregates, they can be used back in the production of concrete, used as a filler material, or these aggregates can again be used for dry cleaning of the concrete drums. So next day or in a couple of days, we can add these to the concrete truck and mix it with the fresh concrete, and they will again make recycle aggregates, which is very good as it reduces the waste. And in my test, I washed the concrete drum for multiple cycles, as these aggregates can be used for multiple cycles without adding more powder, more Recon-Zero powder. So, sorry, why did we needed to test the Recon-Zero aggregates? And now I'm using the term Recon-Zero aggregates for the aggregates produced by using Recon-Zero powder, because as I already mentioned, we wanted to use them back in production. And we wanted to know what is the optimum handling time of these aggregates, or to rephrase, after how many days can we use these concrete back either in production or for dry washing of these concrete trucks. Sorry, before moving further, I will present a video of a dry washing process. So this here in the concrete mixture, we mix a small amount of concrete, simulating some return concrete on the concrete truck. Then we added the Recon-Zero aggregates from previous cycle, and we mixed it for a few minutes. And after some time, the aggregates that we added binded with all the concrete in the drum. The red color is because of the pigment that we added to distinguish between different layers. But the concrete drum is quite clean. Can you see my next slide? Yeah. These are the results from dry cleaning of the concrete drum. As I mentioned, the the concrete drum is quite clean, as you can see on first and third figure, almost shining, and that's without using water. The color on other two are just because of the pigment. The only downside of this dry cleaning with Recon-Zero powder is the concrete attached to the mixing, the blades in the drum. Other than that, we have very small amount of sludge. So yes, we wanted to test the optimum handling time and the abrasion on aggregates due to the process of using these aggregates after 1 or 2 or 3 days, or after a few days into back production. And to test that, we have standard test methods on European, on our EU standards, Microdeval test, Los Angeles test, and Kulle Mulle or Molle method, which is a bit specific for Nordic region, and that is for the determination of resistance to wear by abrasion from studded tires. And I'm pretty sure you all are familiar with this test. As you see that these tests use some amount of steel balls, which are very hard compared to aggregates, and especially our recycled aggregates after just 1 or 2 days of hardening. And they have very high amount of revolutions. So we thought that these tests might be too harsh for our aggregates, but obviously Los Angeles test is very popular and known by everyone, and this test specifically we thought that would be very harsh for the aggregates because of the heavy balls used and high falling height of the aggregates. So first we tested all these different kind of methods, if we can, or different tests, if we can use them. And you see on the figures on Microdeval and Los Angeles test that we lost all the cement mortar that is around these aggregates on the first figure. So conclusion, these two tests are too harsh for the aggregates, and on Molle method we retained the cement paste around the aggregates. So we we decided to go with this test. this is the equipment used for Molle method, which has a diameter of 206 millimeters and some ribs on the inside of the drum, same as Los Angeles test, but it uses a sample of 1,000 gram between 11.2 and 16 millimeters. And 7 kilograms of steel balls are used, and they go through 5,400 revolutions. And we again asked ourselves, and we discussed, is this the right amount? Isn't it too harsh for the aggregates? Because we are the stresses on the aggregates that we are talking about is the handling with a belt loader or a wheel loader, and mixing in the concrete drum and transporting, so the revolutions in the concrete drum. So we thought that this is a bit too harsh for the aggregates. So what we did was we modified the tests a bit. So instead of 5,400 revolutions, we halved it, and we also half the amount of steel balls that is used, and instead of using it underwater, we use it without water, thinking of handling of the aggregates by wheel loader or in the belt, which are in dry conditions. And we just calculated. We just thought that with 2,700 revolutions, if we take an analogy of a concrete truck, which is revolving at max 15 revolutions per minute, that gives us about 3 hours of revolution in a concrete truck. And we thought that is enough time for the aggregates to be tested for in a real life condition. So the pictures on the top is before the test, with modified Molle method, and on the bottom is after the test on the aggregates at the ease of 2 days. And with this method, we tracked the development of strength in the aggregates, or to rephrase, we tracked how much amount of aggregates is retained on a 2 millimeter sieve. And when we plot it, it has a very good correlation with the development of strength of a concrete. And it should be if our test method is working, because the aggregates are basically concrete, which are hardening over time. And this was a very good indication that the test method that we used and modified is again working very good for our purpose. So we used this method, and at the end of 28 days, or at 28 days, we again did this modified Molle method, and we tested the same aggregates on Los Angeles method, because at 28 days they were hard enough to handle all the stresses of this Los Angeles test. And on this curve, or this plot on the right, I plotted the Los Angeles values on line graph, and on the bars are the results from modified Molle method. And the 4 curves are 4 different cycles for these Reconcero aggregates. And again, we see a very good correlation between these 2 methods, suggesting the test method that we used are working very good. And Los Angeles method was not working for aggregates at the early stage of life, which was too harsh, but it's working at 28 days. And the aggregates that we got from dry washing of concrete rock has good properties in terms of abrasive strength. The Los Angeles values were, the Los Angeles coefficient was 25 and less. The only thing that we, the flakiness index was reduced a lot. but it has high water absorption compared to natural aggregates that we use. That's the only issues that we saw with these aggregates, or one of the issues. But that's for other time. Here we are just talking about a different test method that we used for recycled aggregates. So what we concluded from this is this modified Molle method that we used for our test have consistent results. The results are comparable to Los Angeles test at 28 days. Of course, it needs a bit more research on whether the parameters that we modified, for example, the number of revolutions, are realistic or very realistic in terms of the stresses the aggregate goes through in a production plant. That is the next step to do. But in summary, we have a very good test method that is working for our recycled aggregates. And if we move further, we may be able to produce some of these, a table like table 12 on European standards 12620, where we have these rating for the aggregates, and we can do the same for recycled aggregates. Thank you very much. That is my presentation.
Thank you, Deepan. Thank you for the nice presentation. And yeah, we also thinking of using such and the new test methods for the lightweight aggregates, because we face the similar issues with the normal testing methods, that it won't withstand that kind of heavy testing with colorless aggregates. So we are in the process of using Deepan's test method.
Yeah, we can call it the deepened method.
I think so. Yeah, why not?
I just have one thing to add. I would say Iveta's Deepan's method, because Iveta and me were discussing a lot during this process. So I would add Iveta's name in front of me as well.
Generous, okay. I'm not giving my material any other's name, so it's Priya's one. So yeah, let's move on to the next presentation. Oh yeah, okay, sorry, I didn't see that. Okay, Deepan, it's like in the slide of different tests, like Los Angeles, the product looks like have a smooth surface. Is it good to use the aggregates in concrete? I think a thin section may show better understanding about the attached cement mortar within the recycled aggregate. Yeah.
Well, it depends. I think when these aggregates are round, it has a very good handling. When the flakiness index is reduced, it flows better. And that has very good implication on the practical side of handling things. On the strength of concrete, I'm not sure, but my hypothesis is, since the natural aggregates, in their natural shape, they have reacted with the concrete, and there is a layer between aggregate and concrete. And what we are doing by adding these recycled aggregates again in back production is we are if I would say that it should be tested, because I'm not sure which layer or which transition zone is defining the strength of the concrete after we have used this in back production. Is it the natural aggregate and the Recongero interface, or it is the interface between the Recongero and the new concrete? I'm not pretty sure about that. Which one is the? So this is for further research, but in terms of handling, it improves the practical aspect of doing things.
Yeah, I think you mean to say the interfacial transition zone.
Yeah.
Yeah, I think this is similar to any other recycled aggregate which we get from the demolition, construction and demolition as well, because we have the older mortar with one ITZ and also the new mortar which makes one more interfacial transition zone, which is the issue. But yeah, like you said, the workability with granular aggregate, which is also the case with the lightweight aggregate which we produce, which is also like spherical mainly. Yeah.
For tank not as a treatment method for the aggregate. In this case, we want to consume and it's intentionally attached. For the slide within the production, not to get
Yeah.
Yeah, I couldn't hear what.
Okay. Okay, wait, is like further away from me, so you're not hearing. She says that the aim of the work is to reuse the waste, so it's not about producing the high quality aggregate, but to not to make it go to the waste. Instead, we are keeping it running in the cycle of concrete. So, yeah. Yeah, otherwise, yeah, I'm just will produce a lot of sludge. That's what she says. So I think it answers the question from. Okay, so let's go to the next presentation, which is by Victor and Tatiana. They're from Norfu.
Okay.
Okay, now. So they're from Norfu, from Russia, and they would be presenting about integral quality indicators of waste concrete for reuse. So now, Victor, you can take over.
Yeah, Deepan should close.
Yeah, Deepan, I think still you're sharing your screen.
You don't need to. Oh no, it's not saying. I don't know everything. Yeah. It's okay. It should be something here. I will go on. I will go on.
Okay, now it's ready to go. So, my name is Victor Danilov. I'm head of the Laboratory of Composite Materials in Northern Arctic Federal University. And today I have a short presentation about integral quality indicators of waste concrete for reuse. So recycled concrete is one of the main heavy construction waste having good recycling prospects with regards to rational nature management related to reducing the consumption of natural resources. However, widespread introduction of secondary concrete is hindered on the one hand by the variety of composition and structures of recycled mineral raw, and on the other hand by the lack of quantitative criteria to choose the most rational area of the use. For example, we can use coarse aggregates in new concrete. We can use fine, also fine aggregates and concrete powder in different ways, as a binder, as a finely dispersed filler, and so on. Currently, there are various approaches to recommendation for recycled concrete application that are predominantly associated with its use as a coarse aggregate. However, using recycled concrete only as aggregates cannot be considered an optimal way to address the issue of recycling these materials. Oh, and this on the slide there are several ways to dispose: fine, coarse, recycled concrete aggregates, and concrete powder. And one of the most cost-effective in our view is composite binders, calcium carbonate concrete, alkali activated slag concrete blocks. It's for recycled concrete powder. So our aim of the research is an attempt to formulate integral indicators of the quality of recycled concrete that can be used to find the optimal option for recycling. Coarse aggregate, fine aggregate, active middle, additive filler, and so on. But indicators should allow to objectively and unambiguously show which way of disposal is the most efficient and profitable for industry and for business. So we can prove them that it's very profitable to use secondary concrete. These set objects of the study are to assess the activity indicators of recycled concrete powders obtained from lightweight and heavy concrete fragments of a demolished building operated for more than 50 years. And we used several indicators: contraction value, calcium carbonate and calcium hydrosilicate contact, specific surface area and porosity, chemical composition, surface tension, and grindability. Second is to check for correlation between activity indicators of recycled concrete powders and strength properties of composite binders based on FCP, and to check for correlation between coarse recycled concrete aggregates, fraction size, and properties of secondary concrete based on them. So in our case study, we obtain our sample from a demolished residential panel building from Arkhangelsk. As you can see on this slide, it was demolished by the crane, and it's not very efficient and environmental healthy, but it's the most common practice in Russia. And as you can see in the photos, we visit this place, and we take about 100 kilograms of different samples from that object, and also we go inside that house before it was demolished and measure the strength of the different structures by shock impulse method. So we take these concrete samples, and we manually remove the reinforcements, and it was about 2 kilograms of reinforcements from 100 kilograms of reinforced concrete. And as you can see, the sample of lightweight concrete with silica, with ceramics mosaic, and heavy concrete. So it's and also there is insulating mineral insulating material, mostly consists of shungizid. Is a material mainly alumina, silica. It's very porous and light material. So we determine the residual compressive strength of a different sample. Lightweight concrete, it's Kirsten wall panel, Its strength about 20-40 megapascal, and concrete class B25. And heavy concrete have strength, residual cooperative strength about 40 to 60. It's very good actually, and concrete class about B40. And this sample have very high residual compressive strength. So we take the sample and we manually crush them to pieces maximum 120 millimeters in size. Then these concrete fragments were crushed using jaw crusher with hard to pronounce name DC12. So it's Russia jaw crusher. Don't try it at home. Pronounce this name. It's only for Russians. So we use this jaw crusher and we obtain those screens that you can see. And heavy concrete and lightweight concrete. Lightweight concrete also contain a lot of ceramic mosaic and a lot of shungizit is mineral insulation. So next step, screenings were divided into fraction on a standard set of sieves by a dry method. A fraction that passed through the sieve number 014 mesh was selected for further research. Is concrete dust in a nutshell. But looking at this characterization of screenings, we can make one important conclusion. No matter lightweight concrete or heavy concrete, the amount of coarser shear, finer shear, and concrete powder in the crushing products practically does not depend on the strength of the original concrete. So we can grind and mill lightweight concrete and heavy. We will have the same granulometry. So it's a very important conclusion. Then we study the surface tension, and I explain why. The destruction of concrete during crushing occurs mainly along the cement sandstone or along the surface of its contact with a large aggregate. Consequently, when using crushed stone from recycled concrete in concrete mixes, the strength on the new concrete will largely be determined by the adhesion of new cement stone to the old one. The above also apply to concrete powder. The similarity of the values of the components of the surface tension can be used to characterize adhesion of inactive mineral powder systems that can be used as a filler in cement composites, polymer composites, and so on. And we measure the surface tension from concrete powder, lightweight and heavy concrete powder. And it's a lot similar with Portland cement, but heavy concrete powder is even more similar to Portland cement. And the main conclusion from that, heavy concrete powder will have more adhesion in different mixes, new cement mixes. And we also can change values of surface tension of concrete powder by chemical methods, by mechanical activation, and so on. Our goal is to make surface tensions values as much as close to Portland cement, and then adhesion will be maximum. The next approach to assess the use of concrete powder is a Grenability Index. It's not our invention. The authors of the paper, Krashnikova, Hozin, and Morozova, research grindability of different dry mixes, and they propose a quantity grindability criterion, Grenability Index. it's easily calculated. You need 2 specific surface area of powders before and after mechanical grinding during the time delta T. In our case, it was 30 minutes. It's surprisingly that heavy concrete powder have more gradability index than lightweight concrete. And we now know why, because lightweight concrete has this mineral insulation material, fungicide, that's very difficult to grind. It have metal particles, and that's why grindability index is so low compared to heavy concrete. Next, we characterize our concrete powders. You can see strength class of original concrete, true density of powders, the contours of main components in terms of oxides. And as you can see, heavy concrete has more calcium oxides, and lightweight concrete that's more silica oxides, because it's have mineral insulation materials. And specific surface area after we grind these powders in planetary ball mills is also in this table. After that, we measure the we make a thermogram of our lightweight concrete powder and heavy concrete powder to calculate how many calcium carbonate and calcium hydrate inside the powders. So it's very useful because if you want to carbonate these powders as the next step, you need to know how many already inside and how many calcium hydrate to use for carbonation. So it's one of the main criteria. And the next, we make several different composite binders based on Portland cement and recycled concrete powders. The first row is Portland cement only 100%. It has contraction about 3 milligram per gram. Contraction is volumetric deformation of powder system during the hydration. We use this value to predict binder activity, how much strength it will be at 28 days of curing. So Portland cement have binder activity about 42 megapascal, and our powders from heavy concrete and lightweight concrete only 0.28 contraction and 0.35. That's correlate to binder activity about 4 or 5 MPa. That's very low, but we also can use these powders to use it instead of part of the cement. So we make some samples with 10% of cement replaced by these powders. It's the last 2 rows, and we have pretty decent bending strength. And the compressive strength. If we compare them to 100 Portland cement. And also, as you can see, if we use only our powders from lightweight and heavy concrete, it have very different setting start and end of setting compared to Portland cement. And normal consistency is also differ from the cement paste. So it's explain this low, relatively low compressive strength compared to Portland cement. And also, we start to think about coarse recycled aggregates, and we test them using our press, and we measure the strength of crushed stone. In Russia, it is characterized by a grade determined by the crushed stone crushing during compression. In the cylinder, grinding grains depends on the weight lost when testing crushed stone in a water saturated state. We made this test, and heavy concrete with fraction 5-10 millimeters and have the most crushing grade 600 is very high, and it's comparable with natural aggregates, but unfortunately lightweight concrete is not suitable. It's only 300 crushing grade, and it's not very good aggregates. Also, the high water absorption for lightweight coarse lightweight aggregates. And we made concrete samples in the form of cubes with crushed stone 5 millimeters from light and heavy concrete, and used that as an aggregate with the same cement content and equal water cement and water solid ratio. After 28 days of holding under normal curing condition, we test for compressing strength. And the test results show the compressive strength of concrete with crushed stone from waste light and heavy concrete was 15 MPa and 43 MPa respectively. That therefore it can be concluded that the higher the residual strength class of concrete, the higher the strength of new concrete, the final product. And heavy concrete is our result is very, very high for that matter. So the conclusion: the main integral criteria for choosing the rational use of waste concrete produced when demolished building construction after the long-term operation, it is advisable to use the following combination of values. Contraction and calcium carbonate contact, but only for recycled concrete powders, which are planned to be used as active additives, binder, replacement of cement. For powders which are planned to be used as inactive filler, is more importantly to know surface tension, specific surface area, and porosity. And as for coarse recycled concrete aggregate, residual compressive strength will be the main criteria for choosing. And I think that's all. Thank you for your attention. If you have any question, you can ask now.
It's scary to ask question now. But you have a question there. Which test method was used for testing surface tension for fine recycled concrete?
So we used over-K methods, Owens, Wendt, Rabel, and Kerble method, which can used for obtain surface tension, two values of surface tension. I need to show it in the slide. Yes. Slide. Polar and dispersive components of the surface tension. So, for example, last row surface tension, first column is polar compound, second dispersive compound, and the last one is sum of the previous two. And when we research the surface tension, this for concrete powders, we actually know that polar compound is more important, and polar compound of surface tension can predict the adhesion of concrete powder to new concrete. We can use that value. So that's why in the graph it's a polar compound in surface tension.
Hope that answers your question. Is there any more question? And we are also at the end of the seminar. So if you have any questions in any part of today's seminar or more about your project, you can ask now.
Where do you differ between the active binders and non-active, where do you put the line before reactive? Or the binder is called reactive because some binders have very little, some have so. Do you have a measure where you set the line?
It's an interesting question. I'm not sure what value.
That might be answered by seeing so that might be this.
But it's too long to wait for business. If they want to know now, and pre-how test of construction is better, we can make pre-how. We now know construction, and we predict what strength will be in 28 days. It's very fast, and values correlate with real strength. So we can use it. 28 days to 1. Yes, also very.
Okay. Yeah, we have the recording of the session, and those who cannot be here for the whole session or those who can't follow us now, whomever registered, so they will get a link for the recording so they can watch it later. So if that is all, then we will sign off because we are already like 10 minutes late for finishing the seminar. And we are always happy to answer your questions. You can find our contact in our project website, so you can contact us anytime regarding the works that we discussed now. So that's it for today. Thank you. Thanks for being with us for the seminar of Deconcrete. Bye. See you.